Somewhere out there is a hole in space so wide that light would need nearly 200 million years just to cross it. Close your eyes for a moment and picture the darkest place you have ever stood. Maybe it was a field at midnight, far from any city. Maybe it was the inside of a cave, where you waved your hand in front of your face and saw nothing at all. Now let that darkness grow. Let it grow past the edge of your town, past the edge of the earth, past the edge of every star you can name. Let it grow until it swallows entire families of galaxies, whole clusters of light, and still keeps going. That is the kind of darkness we are going to sit with tonight. Astronomers have found regions of space so vast and so strangely empty that they dwarf even superclusters, the largest bound families of galaxies we know. Groups so big they can stretch across hundreds of millions of light years. A void like this can be even larger than that. It can hold almost nothing inside it. No bright spiral galaxies, no soft clusters of ancient stars, just a long, quiet stretch of space where the universe seems to have forgotten to build anything at all. If you drifted into the middle of one of these voids, your body would float in a silence deeper than any silence on Earth. There would be no sound anyway, since space carries no air to carry sound, but even the light would thin out around you. The stars you left behind would fade into faint points, then smudges, then nothing. You would hang there, small and quiet, in a stretch of the universe that looks almost, but not quite, like nothing. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. Cosmologists first began noticing these gaps decades ago, when they started mapping galaxies not just by where they sit in the sky, but by how far away they are. They expected clumps, they expected strings of galaxies strung together like beads. What they found was that alongside those strings, there were also enormous gaps, regions where galaxies simply did not appear. The first time astronomers really understood the scale of one of these gaps, it changed the way we picture the universe. It was not a smooth, even field of stars. It was something more like a sponge or a web, full of dense threads and hollow rooms. We still do not fully understand how those hollow rooms got so large. The early universe, in its first few 100,000 years, was remarkably smooth. Matter was spread out almost evenly, with only the tiniest ripples in density, differences smaller than 1 part in 100,000. Somehow, over billions of years, those small ripples grew into the difference between a supercluster crowded with galaxies and a void with almost none. Gravity pulled matter toward the dense spots and left the thin spots even thinner. That much seems clear, but why some regions became so extremely empty, so much bigger and stranger than we might expect from those tiny early ripples, remains an open question. Some researchers wonder if we simply need better maps, that some of these voids are not truly empty but full of faint, dark galaxies too dim for our telescopes to catch. Others wonder if the emptiness is trying to tell us something deeper about how gravity and cosmic expansion work together at the largest scales. Both ideas stay on the table. Neither one is settled yet. Tonight, we are going to move slowly through this landscape of gaps and threads. We will look at how these voids were first mapped, how big they truly are, and what it might feel like to live inside one. We will sit with the strange fact that the largest structures in the universe are not the bright ones. They may be the dark ones, the ones defined by what is missing rather than by what is there. You do not need to hold on to any of this tightly. Let it drift through your mind the way starlight drifts through the space between galaxies, slow and patient, taking its time to arrive. There is no test at the end of this. There is only the quiet pleasure of wondering about something we have not yet fully solved, while your body rests and your thoughts loosen their hold on the day. Let your breathing slow. Let the dark spaces settle around you like a blanket, wide and soft and mostly unmapped. Close your eyes and picture a map of the night sky. Not a map of stars, but a map of the spaces between them. If you could see the whole universe laid flat, like a quilt pulled tight, you would notice something strange. The bright parts, the parts full of galaxies, would form thin threads and knots. Everything else, and there is far more of everything else, would sit dark and quiet. That darkness has a name. Astronomers call it a void. A void is not a hole punched into space. It is a region where galaxies are few, spread thin, sometimes almost absent for hundreds of millions of light years in every direction. Your body, if it could somehow drift into the middle of one, would float in a silence so complete that the nearest galaxy might be farther away than anything you have ever tried to imagine. Light from that galaxy could take tens of millions of years just to reach you. To understand how big these voids really are, it helps to start small. Our own galaxy, the Milky Way, is large by human standards. Light takes about 100,000 years to cross it. That already strains the mind, but a typical cosmic void can stretch across 100 million light years or more. Some, called supervoids, may reach several hundred million light years across. If the Milky Way were the size of a coin, a supervoid would be the size of a large room. The universe is built like a sponge, though no one designed it that way. Cosmologists describe it as a cosmic web, a pattern of filaments or long thread-like structures where galaxies gather in great chains. These filaments cross at nodes, dense knots where galaxy clusters pile together. Between the threads and knots lie the voids, the empty rooms of this vast structure. Nobody built the pattern on purpose. Gravity built it slowly, over billions of years, pulling matter toward matter and leaving the rest behind. Your instinct might be to think the voids are simply empty, full stop. The truth is a little softer than that. Voids do contain some galaxies, just very few, and they are often small, faint, and hard to find. Some researchers wonder whether many more dim galaxies hide in these regions, too faint for our telescopes to catch. Others think the voids may be even emptier than our current surveys suggest. Once we account for gaps in the data, both possibilities remain open, and that gap between what we can see and what may actually be there is part of what makes voids so quietly puzzling. Distance is measured here in an unusual way. Astronomers often use redshift, a stretching of light that happens as space itself expands, carrying galaxies farther from us over time. The more a galaxy's light has stretched towards the red end of the spectrum, the farther away and the older that light usually is. When astronomers map thousands, even millions of galaxies this way, patterns emerge. Clusters glow bright with light sources. Voids appear as long stretches where the light sources simply thin out and vanish. Age matters too. These structures did not always exist. In the earliest universe, matter was spread almost perfectly evenly, with only tiny differences in density from one place to another. Over billions of years, gravity took those tiny differences and turned them into something enormous. Regions with slightly more matter pulled in more matter still, growing into filaments and clusters. Regions with slightly less matter kept losing what little they had, emptying further as time went on. The voids we see today are not just gaps. They are the shadow of the universe's youngest, quietest moments, stretched and magnified across billions of years. If you tried to walk in a straight line through a supervoid, at any ordinary human walking pace, it would take you tens of billions of years to reach the other side. That is longer than the current age of the universe itself. The scale is not something your mind is built to hold comfortably, and that is all right. Nobody's mind is. What remains genuinely unresolved is not just the size of these voids, but their origin and their true contents. Did small, ordinary fluctuations in the early universe really grow enough on their own to create regions this vast and this empty? Or is something else at work? Some property of gravity or dark energy, the mysterious force linked to the universe's accelerating expansion that we do not yet fully understand. Cosmologists have models, and some of those models agree closely with what we observe. Others still leave gaps. For now, the basic shape of the picture is simple enough to hold in your mind as you drift towards sleep. Threads of galaxies, knots of clusters, and between them, vast quiet rooms of nearly nothing. Your body will never travel there, but your imagination can rest quietly at the edge of one, sensing the scale of a silence that stretches farther than the mind can measure. Picture a spot in the sky near the constellation Boötes, the herdsman. Nothing marks it. No bright star sits there to catch your eye. But if you could travel to that patch of sky and keep going deep, past the stars we can see, you would enter a space almost 250 million light years across that holds far fewer galaxies than it should. Astronomers found it in 1981. They were mapping galaxies, plotting their positions and distances, when they noticed a gap. At first, they found only a handful of galaxies inside a volume of space that should have held thousands. Later surveys found a few more hiding in the dark, but the count stayed strange. Something had scooped out a piece of the universe, or rather, something had never filled it in the first place. Here is the puzzle at the heart of its birth. The early universe, just after the Big Bang, was almost perfectly smooth. Matter and energy spread out evenly, like fine dust stirred through water. Tiny ripples existed in that smoothness. Differences in density so small they measured only a few parts in 100,000. Those ripples are the seeds of everything we see now, including places like the Boötes Void, where almost nothing grew at all. If you had stood in that early universe, your body would have felt no different in one spot than another. The density ripples were far too faint to touch, but gravity does not ignore small differences. It magnifies them, slowly, over unimaginable spans of time. A region with slightly more matter pulled in more matter. A region with slightly less matter lost what little it had to its denser neighbors. Over billions of years, the small became large, and the large became the cosmic web we now map, filaments and clusters laced around vast hollow rooms. One idea about the void's birth is that it grew from a broad, shallow underdensity in that early ripple pattern, a place where the starting deficit was already there, just waiting for gravity to stretch it wider. Matter at its edges felt a gentle, constant pull toward the denser walls around it. Over roughly the age of the universe, that slow drain emptied the middle almost completely, leaving behind a handful of stranded galaxies with vast dark distances between them. A competing idea points to the merging of several smaller voids. In this picture, the Boötes Void did not start as one single low-density patch. It formed from a handful of smaller, ordinary voids that expanded outward and eventually merged into one continuous space, their walls dissolving as the galaxies between them drifted toward larger structures nearby. Both explanations agree on the end result. They disagree on the path that led there, and current surveys have not settled which story fits the evidence better. The scale of time involved is difficult to hold in the mind. This emptiness did not open in a moment. It took billions of years of quiet drift, galaxies pulled ever so slightly by gravity, year after year, gathering into walls while the space between them slowly cleared. If you watched the whole process sped up, you would see galaxies crawling outward from the center, like slow bubbles rising to the surface of a pond, leaving open water behind. What makes the Boötes Void useful to study is its nearness in cosmic terms. Other voids sit farther away, harder to probe in detail. This one is close enough that its handful of galaxies can be examined one by one, their light gathered and studied for clues about what conditions let a few points of light survive at all, in such a wide, quiet gap. Some researchers wonder whether the galaxies found inside are truly native to the void, born there from whatever thin matter existed, or whether they are stragglers, remnants of denser structure that never finished draining away. That question remains open. It touches the larger mystery of whether voids are ever completely empty, or whether they always keep faint traces of the structure they once might have held. Your body, standing in that hollow, if such a thing were possible, would feel weightless and directionless, with no nearby mass to give gravity's pull any clear direction. The nearest large galaxy cluster would sit so far away that its light would have left it long before humans existed. And yet the void itself is not a flaw in the universe. It is a natural outcome of the same process that built every bright filament and cluster we see. The emptiness and the fullness came from the same faint ripples, stretched by the same patient gravity over the same 15 billion years. How that stretching produced such a stark difference between a nearly starless gulf and a galaxy-crowded wall is still being worked out, one survey at a time. Try to picture a distance so large it stops feeling like a number. The Boötes Void stretches almost 330 million light-years across. If you tried to cross it at the speed of light, the trip alone would outlast entire chapters of Earth's own story. Your body would drift for that whole span, through darkness, past nothing that glows, nothing that pulls, nothing that answers back. To hold that size steady in your mind, it helps to think in smaller steps first. Our own Milky Way galaxy is about 100,000 light-years across, already too wide for the mind to picture as a single object. Now imagine 3,000 galaxies like ours, laid end to end in a straight line. That line would still fall short of spanning the Boötes Void just once. This is the strange arithmetic of emptiness. Nothing is not simple. Nothing at this scale has its own kind of size, and that size dwarfs the very galaxies that nothing surrounds. What is actually missing from a space like this? Ordinary galaxies are built from hydrogen and helium, the two lightest elements, gathered slowly by gravity until they burned bright enough to become stars. Inside those stars, heavier elements were cooked over millions of years. Carbon, oxygen, iron, the raw materials of planets and oceans, and eventually of bodies like yours. Day void. is a place where that whole chain of cooking barely got started. Few galaxies formed there, so few stars ever lit up, so few heavy elements were ever built at all. In a real sense, the iron resting quietly in Earth's core and the iron once fused inside some ancient dying star both trace back to a universe that happened to clump unevenly. The Boötes Void marks a place where that clumping simply did not happen much, and the deep question of why is still being worked out. Even here, though, empty needs a careful definition. Voids, like this one, are not a perfect vacuum, with literally nothing inside. They still hold faint traces of hydrogen gas, spread so thin it would take enormous volumes just to gather enough atoms to fill a single room. Some scattered galaxies do drift within the Boötes Void, dim and far apart, like a handful of lit windows in a very large, very dark house. What is missing is not matter itself, but density, the ordinary crowding of matter into stars and galaxies that fills the rest of the observable universe. One idea holds that this thin material inside voids is simply the leftover gas that never found enough gravity nearby to pull it together. A competing idea suggests that some voids may have lost even more material over time, slowly drained toward the denser walls that surround them. Which explanation fits best, or whether both are partly true, remains an open question. Researchers are still testing with new surveys. Scale also changes what gravity can do. Near a filament, where galaxies gather in long glowing threads, gravity has plenty of matter to work with, and it pulls things closer together with real strength. Deep inside a void, matter sits so far apart that gravity's pull grows faint and slow, stretched thin across enormous distances. Some researchers propose that this weak, spread-out gravity is itself part of why voids kept expanding rather than filling in. Others focus on dark energy, the mysterious pressure that seems to push space apart everywhere, and wonder if it acts with extra strength in these already sparse regions. Neither idea has been confirmed as the full picture, and both may be part of a more complicated answer scientists have not yet found. If you floated at the very center of the Boötes Void, your eyes would take real time just to notice anything at all. The nearest galaxies would sit so far away that their light would look like faint, cold pinpricks, and long stretches of your view would show nothing but black. Sound would carry to no one, because there would be no one nearby to hear it. And yet, that same silence is one of the reasons the void matters so much to scientists. Its very size, larger than clusters, larger than superclusters, forces astronomers to ask how such a vast imbalance could grow from a universe that started out nearly smooth in every direction. The building blocks of a void, then, are almost a mirror image of the building blocks of a galaxy. Where galaxies are built from gathered gas, burning stars, and heavy elements slowly forged over time, a void is built mostly from the absence of that gathering, and from a scale so large it stretches simple counting. Understanding why matter chose to crowd in one place and stay scattered in another remains one of the patient, unfinished puzzles of modern cosmology. For now, the void's true size stands as its own kind of fact, worth resting on quietly in the dark. Picture yourself drifting above a dark ocean at night, with only a few scattered lighthouses visible on the horizon. That is close to how galaxies sit inside the universe. They are not spread evenly like sand across a beach. They gather into thin, bright lines and clumps, and everywhere else is water. If you floated far from any galaxy, Your body would hang in a silence, with no light source close enough to warm your skin. The force behind this pattern is gravity, the pull that draws matter toward other matter. Gravity sounds gentle in small doses, like an apple falling from a tree, but across billions of years, gravity becomes patient and relentless. It takes the smallest differences in density, spots in the early universe that were only slightly more crowded than their surroundings, and slowly drags more material toward them. A region with a little more mass pulls in a little more gas. That gas cools and forms stars. Those stars pull in more gas still. Over time, the rich get richer and the empty get emptier. This is why galaxies behave like rare islands in a wider sea. They are not the rule, they are the exception, the places where gravity found enough of a head start to build something bright. Some researchers describe this as runaway collapse, where a tiny seed of extra density becomes, after enough time, a full galaxy cluster glowing across the dark. The seeds themselves seem to trace back to the very early universe, to tiny ripples in the hot plasma that filled space just after the beginning. Nobody fully agrees on why those ripples were arranged the way they were, only that they were there and gravity acted on them. But gravity alone does not explain the whole picture. Pressure worked against it in the early universe, when ordinary matter was locked together with light in a hot, dense fog. Photons, the particles of light, pushed back against gravity's pull, slowing the collapse of matter into clumps. This tug-of-war between pressure and gravity left its own fingerprint on the pattern of galaxies we see today, a rhythm cosmologists still study by measuring how galaxies are spaced across great distances. If you had stood inside that early fog, the light around you would have been so dense that it acted almost like a wall, resisting collapse everywhere at once. Then there is the reach of gravity across empty regions, a subtler kind of shaping. A void does not need matter inside it to feel the pull of matter outside it. The galaxies and clusters that ring a void tug on each other, and in doing so, they slowly draw material away from the void's interior. It's less like emptiness appearing, and more like emptiness being drained toward its edges. Some cosmologists picture this as matter migrating outward from the void's heart, the same way water drains from the center of a basin towards its rim. Your body, if it hovered at the center of one of these regions, would rest at the exact point that gravity had been quietly abandoning for billions of years. Dark matter, the invisible material that outweighs ordinary matter across the universe, plays its own part in this shaping, though its nature remains unresolved. It does not shine, and it does not interact with light the way ordinary matter does. But its gravity is real, and many researchers think dark matter formed the first scaffolding that ordinary gas later fell into, tracing out the filaments and voids we now observe. One idea holds that voids are simply regions where dark matter never gathered enough mass to matter. A competing idea suggests the voids themselves may hold faint, diffuse dark matter that never lit up, invisible not because it is absent, but because it never triggered star formation at all. Neither view has been settled, and the difference matters for understanding whether voids are truly hollow or only truly dark. Across all of this, one force works quietly in the background, on scales larger than any single void. Dark energy, the mysterious pressure that seems to be pushing space itself to expand faster over time. Some researchers wonder whether dark energy stretches voids more aggressively than it stretches crowded regions, widening the gaps between galaxy filaments as the universe ages. If true, the sea between the islands would only be growing wider, gradually, invisibly, while nothing anyone could see would seem to be happening at all. The question remains open, resting quietly in data that is still being gathered. So the emptiness is not passive. It is being sculpted. In the same slow way, a canyon is sculpted by water that no one is watching. Gravity gathers, pressure resists, dark matter scaffolds, and dark energy stretches. Somewhere in the balance of these unseen forces, the islands of light we call galaxies keep drifting further apart from each other, adrift in a sea that keeps quietly growing. Picture a house with only a few rooms furnished and all the rest left bare. That is one way to imagine the cosmic web, the largest pattern we know of in the universe. Galaxies gather along thin, glowing filaments, like furniture pushed against the walls of a vast, mostly empty house. Between those filaments lie the voids, the bare rooms, stretching for distances the mind can barely hold. If you lay down in one of those rooms, you would feel how much space is simply unclaimed. To understand the scale, start small. Our galaxy, the Milky Way, holds a few 100 billion stars, packed into a disk about 100,000 light-years across. That already strains the imagination. But the Milky Way is just one grain of sand on a beach. It belongs to a small cluster of galaxies, called the local group, which belongs to a larger structure, called the Virgo supercluster, which itself is only a minor branch of an even larger structure, called Laniakea. Each step outward multiplies the distance by 10, sometimes 100. Now picture shrinking all of Laniakea, that enormous supercluster complex, down to the size of a dinner plate. On that scale, the Boötes Void, one of the largest known empty regions, would still be roughly the size of a small house. That single void is estimated to span about 250 million light-years. Light, moving at its steady, unmatched speed, would need 250 million years just to cross it. Your body, standing anywhere inside that space, would be surrounded by darkness in every direction, with the nearest galaxies farther away than almost anything you have ever tried to picture. Compare that to something more familiar. Light from the sun takes about 8 minutes to reach Earth. Light from the next nearest star takes about 4 years. Light from the edge of the Milky Way takes about 100,000 years. And light crossing the Boötes Void alone would take 2,500 times longer than that. The numbers do not just grow, they leap, each step outward dwarfing the one before it, like a whisper swallowed by an ocean. Some voids are even larger. Certain supervoids, broad regions of underdensity found in modern sky surveys, may stretch over 1 billion light-years across. If you tried to walk that distance at the speed of light, you would still be traveling long after every star visible in tonight's sky had changed, aged, or gone dark. Your lifetime, and many lifetimes stacked end to end, would not be enough to cross it. And yet, against this immensity, the actual amount of missing matter is subtle, not simply absent. Voids are not perfect vacuums. They contain some matter, just far less than the average density of the universe. Sometimes 10% as much, sometimes even less. It is less like an empty room and more like a room where almost everyone left, but a few chairs remain scattered near the doorway. The mystery is not simply that these spaces exist, but why they became so consistently, dramatically underpopulated compared to their surroundings. One idea, well supported by both observation and simulation, describes voids as regions where gravity had less to work with From the very start, even in the early universe, tiny variations in density existed, some patches slightly denser, some slightly emptier over billions of years. Gravity amplified those small differences, pulling matter toward the denser patches and leaving the sparser patches even more sparse. In this view, a void is not a wound in space, but simply the outcome of a slow, patient sorting process written into the universe from its earliest moments. A competing question remains open, though. Some researchers wonder whether the scale of these voids, especially the largest supervoids, is fully explained by that gradual sorting alone, or whether other factors, perhaps tied to the behavior of dark energy, the mysterious force linked to the universe's accelerating expansion, may have widened these regions faster than standard models predict. The debate is not about whether voids exist. It is about whether their true size, some spanning distances that dwarf entire superclusters, fits comfortably within our current understanding, or whether it hints at something we have not yet measured correctly. If you tried to hold all of this at once, the numbers, the light years, the near emptiness, your mind would likely resist the scale, the way your eyes strain trying to see something too far to focus on. That difficulty is not a failure of imagination. It may be the most honest response there is. The universe, it seems, built empty rooms far larger than the furnished ones, and we are still learning how and why so much space came to hold so little. Picture yourself floating at the edge of a great void, watching a single beam of light begin its crossing. That light left a galaxy on the far wall of the void billions of years ago, and it has been traveling ever since. Your body would feel no wind here, no pull, nothing but a faint gravitational hum too small to notice. The dark around you would stretch so far that your eyes would struggle to find anything to focus on at all. That beam of light has a long way to go. A void, like the ones astronomers study, can stretch over 100 million light years, from wall to wall. Some stretch even farther. The light crossing this space passes through almost nothing. There is no dust to scatter it, no gas cloud to slow it, no star to bend its path with gravity. It travels in nearly a straight line through what may be the closest thing to true emptiness the universe has to offer. But nearly is the key word, and this is where the mystery deepens. Even the emptiest voids are not perfectly empty. Faint threads of gas drift through them, so thin that the atoms are spread out far more than in the best vacuum any laboratory on Earth has ever built. A stray galaxy sometimes appears, small and dim, sitting alone in the dark, like a lit window in an empty field. Astronomers still debate how many of these lonely galaxies exist, and whether we have found them all. Your eyes, if you could somehow see across this whole space at once, would catch only scattered points of light, thin and far apart, swimming in black. The light crossing the void is doing something else too, something that has nothing to do with what it passes through and everything to do with the space itself. As the beam moves across the void, the space in front of it keeps stretching, gently and steadily, because the universe itself is expanding. This stretching pulls at the light and shifts its color slightly toward the red end of what we can measure, a small clue that helps astronomers judge distance. Some researchers think voids might stretch space faster than the crowded regions around them, since there is less matter here to slow the expansion down. Other researchers are more cautious, pointing out that the difference, if it exists, is subtle and hard to separate from ordinary cosmic expansion. The question of whether voids grow at their own special pace remains open. If you tried to trace this beam of light back to its source, you would be looking across a distance so vast that the number itself starts to feel unreal. Light, moving at its full speed, unblocked by anything, still needs enormous stretches of time to cross one of these regions. Standing here, your body would exist inside a kind of stillness that has almost no parallel back on Earth. No sound could travel through this thin material anyway, since sound needs something dense to move through, and this space offers barely anything at all. The walls of the void, if you turn to look at them, would show you something different. Galaxies bunch up there in soft, faint clusters, the beginnings of the great filaments that thread through the whole universe. From your position in the middle of the emptiness, those walls would look impossibly distant, thin lines of light hanging at the edge of your vision. Some scientists wonder if the void is actively pushing matter toward those walls, a slow, gravitational herding that thins the middle over billions of years. Others lean toward a different picture, where the walls simply grew first, pulling material away from the space between them, leaving the void hollow almost by default. Both ideas try to explain the same texture we see when we map these regions, and both remain unproven in their fine details. What we do know is that the light we study from these voids carries real information, faint as it is. It tells us about the gas that drifts there, about the rare galaxies that formed against long odds, and about the stretching of space itself. It does not yet tell us why the void formed exactly where it did, or why some voids are deeper and quieter than others. If you stayed in this space long enough, you might begin to feel time itself move strangely, stretched thin, like the light crossing toward you. The silence would settle into your body, the way a held breath settles before sleep. Somewhere beyond the dark, a single point of starlight would still be traveling toward your eyes, patient and unbothered, carrying a story from a wall of galaxies so far away that its age is hard to hold in your mind. If you tried to measure the size of a void with a ruler, you would fail before you began. There is nothing to press the ruler against, no wall, no floor, no faint mist to mark an edge. Astronomers had to find another way to measure emptiness, and the method they settled on is quiet and clever. It rests on something called redshift, and it lets scientists measure distance across a place with almost nothing in it. Redshift is what happens to light when its source moves away from us. The light stretches and it shifts towards the red end of the color spectrum, the same way a siren sounds lower in pitch as a car drives away. The universe is expanding, so almost every distant galaxy shows this reddening. The farther away a galaxy sits, the faster it seems to recede, and the more its light stretches toward red. If you watch this light arrive, you would be watching a message that has traveled for hundreds of millions of years just to reach your eye. To map a void, astronomers do not look at the empty space directly. They look at the galaxies that ring its edges. Each galaxy gets a redshift measurement, which gives its distance. Each galaxy also gets a position on the sky, its coordinates among the stars. Combine distance with position, and a galaxy stops being a flat dot on a photograph. It becomes a point floating in 3 dimensions, placed correctly in the depth of space. Do this for hundreds of thousands of galaxies, and a shape starts to emerge. It looks something like a sponge, or a loaf of bread full of air pockets. Dense filaments of galaxies form the walls and threads between them, stretch the voids, revealed not by anything sitting inside them, but by the absence of galaxies where galaxies should be. This technique is called a redshift survey, and it turned emptiness into something you could actually plot on a map. The first large redshift surveys in the 1980s stunned the astronomers running them. One team, tracing galaxies within a slice of sky, expected a fairly even scatter of points. Instead, they found long walls of galaxies wrapped around gaping holes. The Boötes Void showed up clearly in that early data, a great blank stretch where the expected dots simply did not appear. It was one of the first times a void's true size became visible in careful, measured numbers rather than rough impression. Measuring depth this way carries real difficulty. Redshift tells you a galaxy's velocity away from us, and that velocity mostly comes from cosmic expansion. But galaxies also drift a little on their own, pulled by nearby gravity, pulled toward walls of matter, or away from empty stretches. These small extra motions blur the picture slightly, stretching some structures and squeezing others in the data. Astronomers call this effect redshift distortion, and they have to correct for it carefully before trusting the shapes that emerge. There is also the challenge of knowing when a void is truly empty, rather than simply undersurveyed. A patch of sky with few detected galaxies might hold real emptiness, or it might hold faint, small or dust-covered galaxies that current instruments cannot see well. One idea holds that many voids are close to their true emptiness, with only the faintest dwarf galaxies scattered inside them. A competing idea suggests that better instruments, especially ones sensitive to dim infrared light, will keep finding more hidden galaxies tucked into what looked like nothing. Both possibilities remain on the table, and only deeper surveys will settle which one is closer to the truth. If you drifted slowly into the heart of a mapped void, your instruments would report the same story astronomers already suspect. Galaxy counts would drop steadily, then almost vanish. The redshift measurements around you would grow sparse and strange, points of light so far apart that each one felt like a lonely signal fire in the dark. Your sense of depth would come only from those distant fires, not from anything nearer. This method of mapping by absence has shaped nearly everything we know about voids. It has let scientists estimate that some voids stretch across hundreds of millions of light years, and that supervoids can span even farther, close to 1 billion light years in places. These numbers rest on chains of careful measurement, correction, and interpretation, not on any direct touch. Every void map is really a map of light that did arrive, used to outline the far larger space of light that never had a galaxy descended. The nothing is defined by everything just outside its edges, and that boundary remains one of the strangest kinds of measurement in all of astronomy. Picture yourself floating at the center of a great void, far from any bright filament. Your eyes would search the dark for a long time before finding anything at all. But absence to the eye is not the same as absence in truth. This is where the question turns strange. A void is defined by what we can count, and counting depends on what our telescopes can catch. Some galaxies are simply dim. A small, faint galaxy, made mostly of gas and dark matter, with only a scattering of stars, can slip past even careful surveys. Astronomers call these low surface brightness galaxies, and they are hard to see even in crowded regions of the sky. Inside a void, where every patch of space already holds so little, a handful of these faint smudges could easily go unnoticed. Your body, drifting through that space, would pass near objects too dim for your own eyes to register, ghostly and unlit against the deeper black around them. This raises a real possibility. Are voids truly empty, or are they simply under-surveyed? The Boötes Void, which you have already heard called silent and vast, has in fact turned up a small number of faint galaxies. As instruments improved over the decades, each new survey has found a few more than the last. This pattern makes some researchers wonder whether the void is not a hollow shell, but a thinly populated room, one whose true population we have only begun to measure, that there is a competing view, and it deserves equal weight. Other astronomers argue that even with the deepest surveys, the numbers in voids remain far below what the surrounding filaments show. The gap is too large to explain away with mist-faint galaxies alone. In this view, voids are genuinely underdense regions of matter itself, not just regions with dim inhabitants. The dark matter scaffolding that normally pulls gas together to form stars may simply not be present there in the same amounts. If that is true, no amount of better instruments will fill the void with hidden galaxies, because there is less raw material there to begin with. This tension between "we have not looked well enough" and "there is genuinely less to find" is one of the quieter mysteries in cosmology. It does not resolve easily, because proving a true absence is far harder than proving a presence. You cannot simply point to nothing and call it confirmed. Every void survey must ask whether its telescopes are sensitive enough, whether its wavelengths are the right ones, whether some galaxies hide behind dust or drift in orbits that carry them briefly beyond view. There is also a cyclical rhythm to how we search. Each generation of telescopes reopens the question. Radio surveys sweep for the gas that fuels new stars, since even a starless cloud of hydrogen would show up in these frequencies. Infrared surveys catch heat from older, redder stars that visible light might miss. Every new wavelength is like opening a different set of eyes onto the same silence, and every time we do, the void gives up a few more secrets. This has happened again and again since the Boötes Void was first mapped in the late 1970s. The count of galaxies inside it has grown slowly, survey after survey, without ever closing the gap completely. If you lingered at the center of such a void long enough, your instruments would eventually catch the faint radio hiss of trace amounts of hydrogen gas, spread thin, cold, and mostly undisturbed. You would not find nothing. You would find very little, spread across enormous distance. Whether that very little hides more structure than we currently know, or whether it represents close to the true material limit of the region, remains an open question that each new telescope tries to answer. Some researchers propose that dwarf galaxies, small and dim by nature, might be scattered through voids in far greater numbers than we assume, simply below our detection threshold, given current technology. Others counter that computer simulations of cosmic structure, built from our best understanding of gravity and dark matter, predict almost exactly the sparse populations we already observe. If the simulations already match the sparse count, some argue, there may be little room left for large numbers of hidden galaxies. Neither side has closed the case. The void keeps its secrets at a pace set by our tools, not by any fixed answer waiting to be uncovered. Your body, resting in that hush, would be surrounded by a darkness that might hold a little more than it shows, or might be nearly as empty as it appears. For now, the honest answer is that we do not fully know, and each new observation simply narrows the range of what could still be hiding in the quiet. Picture yourself floating near the edge of a great void, close enough to see one last galaxy filament fading behind you. Your body would feel no wind, no pull of air, nothing but the faint tug of gravity from far away. And if you watched carefully, you would notice something odd. The matter around you is not just sitting still. It is drifting slowly away from the emptiness at your back. This is one of the quieter parts of the Void story. Galaxies near the edges of these vast hollow regions do not stay where they are. They move over billions of years. Galaxies at the border of a void tend to drift outward, pulled by the gravity of the denser filaments and walls that surround the emptiness. It is as if the void gently pushes its neighbors away. What is really happening is subtler. The emptiness itself has less gravity to hold anything back. So galaxies near the edge feel a stronger pull from the crowded regions ahead of them than from the near-nothing behind them. Slowly, over cosmic time, they lean toward the walls and away from the gap. Some researchers describe this as a kind of cosmic outflow. Picture a void as a great low place in a gravitational landscape, though not literally a landscape you could stand on. Matter, near its edges, rolls toward the higher ground of filaments and clusters, the way water finds its way out of a shallow basin. Your body, if it could feel this motion, would sense nothing sudden. The drift happens over spans of time so long that no single human life, or even 10,000 human lives, could notice it happening. It is a slow leaning, not a rush. This matters for the larger question of how voids came to be so large and so empty. If matter is still draining away from these regions even now, that suggests the voids we see today may have started smaller and grown as their neighbors pulled away from them. The early universe, as best we can tell from its faint background glow, was remarkably smooth. The density differences that seeded galaxies and voids alike were tiny, fractions of a percent in some regions compared to others. And yet, those tiny differences seem to have grown over billions of years into regions with almost no galaxies at all, bordering regions thick with them. The slow drift of matter away from empty spaces is one piece of how that could happen. Small starting differences, amplified by gravity acting patiently over enormous time, become enormous later differences. This is one working idea. It is not the whole answer. A competing question complicates the picture. If matter is always draining from voids toward filaments, why do voids not simply become perfectly empty over time? Some cosmologists wonder whether there is a limit to the process, a point where a void becomes so underdense that there is almost nothing left to pull away. Others suggest that new material, however faint, might still be falling into voids from unexpected directions, replacing what drains out, keeping them in a kind of slow equilibrium rather than steadily emptying toward nothing. The evidence here is incomplete. Galaxy surveys can track the general motion of galaxies near void edges, but sorting local drift from the larger expansion of the universe itself is a delicate task, one that depends on careful assumptions researchers do not all agree on. There is also the question of neighbors in a more direct sense. Voids do not exist alone, floating separately from one another. They touch. They share walls with filaments, and often with other voids nearby, forming a great connected structure, sometimes called the cosmic web. What drains from one void may, in some models, help feed the growth of a neighboring wall, which itself may border yet another void further on. In this sense, no empty region is truly isolated. Its edges are always in conversation, gravitationally speaking, with what lies just beyond them. If you drifted along this boundary for a long while, your body would stay wakeless and calm, the same silence surrounding you at every point, but you would be moving, slowly, without ever feeling it. carried along with everything near you toward the thicker structures ahead. The void behind you would not vanish. It would simply keep losing its most loosely bound residents, one gentle drift at a time, over a stretch of years longer than we can easily imagine. Whether this outward drift is the main reason voids grew so large, or only one part of a much larger process, remains an open question. The mystery does not lie in whether matter moves near these boundaries. It clearly does. The mystery lies in whether that quiet drift, multiplied across billions of years, is enough on its own to explain regions of space so vast, so empty, and so strangely well organized. If you sat quietly at the center of a great void, gravity would still be reaching you. It would come from far away, from galaxies you cannot see, pulling on the space around you in ways too slow and faint to ever feel. This is one of the strange truths about emptiness in the universe. Nothing here is ever truly cut off from everything else. Let's talk about extremes for a moment, because voids hold some of the biggest numbers in all of cosmology. The Boötes Void, which we met a few sections ago, stretches about 250 million light-years across. That is already hard to picture. But some surveys have found evidence for supervoids even larger regions of the cosmic web, with far fewer galaxies than expected, spanning distances that make the Boötes Void look almost modest by comparison. One candidate, sometimes linked to a cold spot in the ancient afterglow of the Big Bang, may stretch for over 1 billion light-years. Your body, if it could somehow drift through a space like that, would cross a distance so vast that light itself would need more than 1 billion years to make the same trip. Here is where the extremes get strange. Even inside these enormous hollow regions, gravity does not simply switch off. Every galaxy at the edge of a void still pulls, faintly, on everything inside it. Every filament of matter surrounding the void tugs on the thin scatter of galaxies within. The pull is weak, spread thin across unimaginable distances, but it never fully disappears. Some researchers describe voids as regions where gravity is outmatched, not absent. The pull from a nearly empty center is so much weaker than the pull from the crowded walls around it, that everything inside seems to be gently, slowly pushed outward. Matter does not just sit still in a void, it drifts towards the walls, like water settling toward the low points of a landscape, shaped by forces too large to see all at once. This raises one of the strangest open questions in the study of voids. If gravity from the crowded edges is always winning against the emptiness in the middle, why do voids keep growing instead of slowly refilling? One idea points to dark energy, the mysterious pressure that seems to stretch space itself. Some cosmologists propose that in regions with very little matter, dark energy's expansive effect faces almost no resistance. So voids may expand a little faster than the average expansion of the universe. If your body floated at the center of one, you might feel, in principle, the faint pull of walls farther away in every direction, and the faint push of expansion trying to carry you apart from them at the same time. Neither force would ever announce itself with any drama. Both would remain silent, patient, and almost impossibly slow. Not every researcher agrees on how strong this void expansion effect really is. Some simulations show only a modest difference between how fast voids grow and how fast the rest of the universe expands. Others suggest the difference could be larger, especially in the very largest supervoids, where the pull from surrounding structure is weakest. The evidence remains incomplete, drawn from surveys that must measure the positions and speeds of galaxies across billions of light years. using redshift, the stretching of light as galaxies move away from us. Small uncertainties in these measurements can shift the picture considerably. Then there is the question of temperature, which brings its own quiet extreme. The cold spot, linked to some supervoids, appears in the cosmic microwave background. The faint radiation left over from the early universe, photons, passing through a supervoid may lose a small amount of energy, a process tied to the changing shape of space. As they cross such an enormous underdense region, this would make the light look very slightly cooler by the time it reaches us. If this explanation holds, it would mean some of the coldest light in the sky has been shaped not by anything burning, but by the long, slow crossing of almost nothing at all. Other researchers argue the cold spot may be a simple statistical fluctuation, and the debate continues without a clear resolution. None of these numbers, distances, or temperatures answer the deeper question of why the universe organized itself this way in the first place. They only sharpen it. A void hundreds of millions of light years across, shaped by gravity too weak to overcome expansion, cooling starlight by the faintest possible degree. It feels less like emptiness and more like a slow argument between forces we still do not fully understand. If you could hold still at the center of one, you would feel nothing pulling you anywhere in particular, and that stillness itself would be the mystery worth wondering about as you drift toward sleep. Picture a bar of soap worked into a thick lather in your hands. The foam is made of countless small bubbles, each one round, each one pressing against its neighbors. Where 3 or 4 bubbles meet, the walls between them grow thin and bright. Where a bubble stands alone, its wall stays smooth and full. If you look closely enough, you would see that the foam is not really about the bubbles at all. It is about the thin films that hold the air inside them apart. Cosmologists use this same picture to describe the universe. The galaxies gather along the thin films, the walls where one bubble of emptiness presses against another. The voids are the air inside each bubble, vast and quiet, holding almost nothing. If you shrank yourself down and floated inside the foam of the cosmic web, you would drift for a long time along a curved, empty wall, before reaching a place where 3 or 4 such walls met, and galaxies clustered like beads of dew. This bubble picture is not just a comforting comparison. It comes from real maps, built from galaxy surveys that plot the positions of hundreds of thousands of galaxies across the sky. When researchers plotted those positions in 3 dimensions, the pattern was not scattered evenly, and it was not clumped into one shape either. It came out looking like foam, sheet after curved sheet of galaxies wrapped around emptiness. Some describe it as the largest structure ever seen, made mostly of the absence of structure. The thin walls of this cosmic foam are called filaments and sheets, and they hold a strange kind of thinness. A wall in a bubble bath might be only a few molecules thick, and it still holds its shape because of surface tension pulling it taut. The walls of the cosmic web are held by gravity instead, pulling matter sideways into place, even as it also pulls matter forward, toward the densest points, the nodes where filaments cross. Some researchers picture these walls as sheets of galaxies only a few million light-years thick, stretched across void mouths that yawn open for hundreds of millions of light-years on either side. Your body, if it could somehow stand at the edge of one of these sheets, would find almost nothing on one side and a crowd of galaxies pressing close on the other. A border with no fence, no signpost, just a slow thinning of light. One quiet detail that some cosmologists find beautiful is how orderly this foam looks, despite how chaotic its beginnings were. The early universe held only tiny differences in density, ripples too small to see even in the most detailed images of the ancient afterglow of the Big Bang. Yet gravity took those small ripples and, over billions of years, sorted the universe into bubbles and walls, with a geometry that echoes ordinary foam. Some researchers see this as evidence that a few simple physical rules, repeated across enormous stretches of time, can produce patterns that look intentional, even though no one designed them. Not everyone agrees the bubble comparison should be taken too literally, though. Soap bubbles obey the physics of thin films and air pressure, forces that have nothing to do with gravity or the stretching of space itself. Some cosmologists prefer to describe the cosmic web using the language of sponges instead, since a sponge has both empty pores and connected walls in every direction, without a single bubble ever standing fully alone. The disagreement is not really about which metaphor is prettier. It is about which one gets closer to the true, tangled math of how matter has spread itself across the universe. Math that even now resists a fully clean description. What stays constant across every version of the picture is the thinness of the walls compared to the size of the rooms they enclose. A wall of galaxies might stretch across a portion of the sky wider than the full moon appears from Earth, and still measure only a small fraction of the depth of the void beside it. If you traveled at the speed of a spacecraft, crossing one of these walls would take a blink compared to crossing the emptiness on either side. Your journey through a void would stretch on and on, past faint smudges of distant light, before another wall finally rose ahead of you. No one has fully solved why the universe organized itself this way, instead of some other way, with different bubble sizes or different wall thicknesses. Some suspect the answer lies buried in the earliest fractions of a second after the Big Bang. Others think the full answer will only come from watching how these walls and bubbles continue to change ever so slowly as billions more years pass by. Picture yourself floating far above the plane of the sky, looking not at stars but at the oldest light there is. This is the cosmic microwave background, the faint afterglow left over from the early universe. Your body would feel nothing. No wind, no warmth, just the quiet pull of curiosity toward a pattern that has puzzled astronomers for 2 decades. In 2004, scientists working with data from the WMAP satellite, a spacecraft built to measure tiny temperature differences in this ancient light, noticed something strange. Most of the sky showed small, expected variations, warmer and cooler patches scattered in a fairly even pattern. But in one direction, toward the constellation Eridanus, there sat a patch far colder and far larger than the models predicted. Astronomers began calling it the CMB cold spot. At first, many assumed it was a simple mistake. Instruments fail, data gets noisy. Foreground light from our own galaxy sometimes bleeds into readings meant to capture something far older and farther away. Teams checked and rechecked the calibration. They compared it against results from the Planck satellite, a later and more precise instrument launched by the European Space Agency. The cold spot did not disappear. It held steady, stubborn, and strange, refusing to be explained away as a glitch. If you had been one of those researchers staring at printouts of temperature maps at 2 a.m, you would have felt that particular chill scientists know well, the moment when an error you expected to find simply is not there. One idea offered to explain the cold spot connects it directly to our story about voids. Some researchers proposed that this cold patch is not a flaw in the early universe at all, but a shadow cast by something much closer to us. Cosmically speaking, light traveling toward Earth from the cosmic microwave background has to pass through billions of years of space on its way here. If that light happens to cross an enormous void along its path, something interesting can happen to it. As light enters a void, it gains a small boost of energy falling into the mild dip in space that surrounds any large structure. As it climbs back out, moving away from that same void, it should lose that boost again, evening out in a universe governed only by gravity. But dark energy complicates this simple picture. Some researchers wonder whether the accelerating expansion driven by dark energy prevents that energy from being returned in full. Light, passing through a very large, very deep void, might exit slightly cooler than it entered. This effect is called the integrated Sachs-Wolf effect, a name borrowed from the physicists who first described how light shifts in energy while crossing changing gravitational terrain. If this explanation holds, the cold spot in the sky might be evidence of an enormous supervoid sitting along that line of sight, a void so vast it could rival or exceed the size of anything else we have mapped. Teams using galaxy surveys did find some evidence of an underdensity in that direction, a region with fewer galaxies than expected. For a while, it seemed the mystery might close, that the picture is not settled. Later analysis raised doubts about whether the supervoid found in that direction is actually large enough or empty enough to produce a cold spot this pronounced. The math did not fully agree. Some researchers now think the cold spot may need a different explanation entirely. Perhaps a statistical fluke, an unlikely but not impossible alignment of ordinary variations. Others keep looking for a bigger or deeper void hiding in that patch of sky, one that current surveys have not yet fully mapped. You would not see any of this with your own eyes, floating in that dark quiet. The cosmic microwave background is invisible to us without instruments tuned to microwave wavelengths, well outside what human vision can detect. Yet in that region of sky, something real is happening to light that has traveled for over 13 billion years, and researchers still disagree about exactly what. This unresolved question sits at the center of our larger story. If voids can leave fingerprints on the oldest light in the universe, then mapping them becomes a way of reading the universe's memory tracing, where matter thinned out long before galaxies existed, to mark the difference. But if the cold spot turns out to be something else, an odd coincidence rather than a shadow, then the voids remain a separate puzzle, one connected only by comparison rather than cause. Your body rests here, in the dark, weightless, while astronomers continue debating a single cold patch of ancient light, still uncertain whether it is a window into something vast and empty, or simply a fluke the universe left behind by chance. If you drifted into the Boötes Void tonight, your eyes would slowly adjust to less and less light, until you floated in a darkness that felt almost complete. But almost is the word that keeps cosmologists awake. Not every void is empty in the same way, and that simple fact still puzzles the people who study them. For a long time, the word void suggested total absence, nothing there, a hole punched clean through the universe. The truth turns out to be stranger and quieter than that. Most voids do hold a few galaxies, scattered thin, like a handful of seeds thrown across an empty field. The Boötes Void itself, roughly 250 million light-years across, has a small number of known galaxies drifting inside it, far fewer than a region that size should ever contain. Your body, if it hung there in the dark, would still be able to see a faint smear of light if you waited and watched a certain patch of sky. Not nothing, just very, very little. That distinction matters. Some voids appear to be almost perfectly hollow, containing barely a trace of luminous matter. Others seem to hold thin filaments running through them. Faint bridges of galaxies connecting one wall of the void to another, like threads left behind after someone pulled the fabric apart. Astronomers, using large redshift surveys, which map galaxies by measuring how their light stretches as they move away from us, have found this pattern more than once. It raises a quiet question. If voids differ this much from one another, are they really the same kind of structure, or several different things that happen to look alike from far away? One idea holds that voids are simply different sizes at different stages of the same process. A young void might still carry wisps of matter that have not yet drained away. An older, more mature void might have had more time for its matter to migrate outward, pulled by the gravity of the dense walls around it, leaving the center almost bare under. This view, emptiness, is not a fixed state. It is something that deepens with time, the way a bowl empties slowly as its contents settle toward the rim. A competing idea suggests the differences run deeper than age. Some researchers wonder whether the initial conditions of the early universe, the tiny density variations present just after the Big Bang, were not perfectly uniform in how they collapsed or failed to collapse. If that is true, some voids may have started emptier than others from the very beginning, shaped by fluctuations we still cannot fully model. The evidence is not settled either way. Both explanations remain open, and it is possible that both play some part. There is another surprise tucked inside this question. Voids are not silent to gravity, even when they are silent to light. Galaxies, near the edge of a void, tend to drift slowly outward, away from the void center, pulled by the greater mass sitting in the walls and filaments beyond it. This means a void is not simply a place where nothing happens. It is a place quietly losing what little it has, matter seeping toward richer neighborhoods over billions of years. If you could press your palm against the dark here, you might imagine you were feeling stillness. What you would actually be sensing, if gravity was something you could touch, is a slow outward hemorrhage measured across cosmic time. This raises yet another puzzle. If voids are always losing mass to their surroundings, why do some still contain isolated galaxies at all, sitting stubbornly in the middle of all that emptiness? One possibility is that these galaxies formed early, before the void had fully carved itself out, and simply got left behind, islands stranded by a retreating tide. Another possibility is that our surveys are incomplete, and some void galaxies remain undetected simply because they are faint, small, and difficult to see across such enormous distances. Both explanations remain live, and neither has fully closed the case. What makes this section of the mystery so quietly unsettling is how ordinary the word empty turns out to be. It hides a great deal of variation, a great deal of history, and a great deal of motion we cannot directly observe. Voids are not blank pages. They are unfinished sentences, each one written a little differently, each one still being edited by gravity across timescales longer than any human life. If you floated at the center of one tonight, the silence around you would feel absolute, but somewhere at the edge of your vision, faint and almost apologetic, a small galaxy might still be sitting there, quietly refusing to leave. Picture yourself floating at the center of a super void, watching two galaxies drift apart on either side of you. They are not moving through space, so much as the space between you and them is quietly stretching. Your body would feel nothing, no wind, no pull, no sound at the distance behind you, and the distance ahead of you would both be growing, slowly, the way bread dough grows as it rises. This is the strange partnership between two things that shape every void in the universe: gravity, which pulls matter together, and dark energy, a mysterious force tied to the expansion of space itself, which pushes everything apart. For most of cosmic history, gravity has done the heavy lifting. Matter clumped, filaments formed, galaxies gathered into clusters, and voids emptied out as material drained toward denser neighborhoods. At roughly 5 billion years ago, something shifted. The expansion of the universe, which had been slowing under gravity's pull, began to speed up instead. Cosmologists call the cause of that speeding up dark energy, though the name is really just a label for something we do not yet understand. Whatever it is, its effects reach into every void, and some researchers wonder if it reaches there most powerfully of all. Here is one idea. Inside a void, there is less matter, so gravity is weaker there than in a filament or a cluster. If dark energy pushes everywhere with roughly equal strength, then in a region where gravity is too weak to fight back, the push may win by a wider margin. Under this view, voids would not just stay empty, they would actively grow, expanding faster than the average rate of the universe, like an air bubble, expanding faster than the water around it. Some simulations support this picture, showing supervoids swelling in volume over billions of years, while their walls thin out further with time. But the picture has a rival. Other researchers argue that voids expand mostly because of what happens at their edges, not because of any special local behavior of dark energy inside them. In this view, matter along the void's boundary keeps draining outward toward filaments and nodes, the way water at the edge of a draining basin flows toward the plug hole. The void deepens simply because its edges lose mass over time. Dark energy's role becomes background music here, shaping the overall stage but not directing the specific choreography of any one void. Both explanations remain live possibilities, and distinguishing between them requires measurements precise enough to catch subtle differences in expansion rate across enormous distances. If you could listen closely enough, you would hear these two explanations arguing quietly in the data astronomers collect. Weak gravitational lensing, the slight bending of light from background galaxies as it passes near a void, offers one way to test the difference. So does counting how the number of galaxies at a void's edge changes across cosmic time. Neither method has settled the question, and both require surveying enormous swaths of sky to gather enough voids for a fair comparison. Your body, if it could travel between 100 different voids, would notice no difference between them by feel alone. The differences live in the math, in redshift measurements, in patient statistical work, stretched across years of observation. There's a deeper reason this connection matters. If voids truly do expand faster because of dark energy, they become a kind of natural laboratory, a place where the effects of this mysterious force show up more clearly than anywhere else in the universe. Some cosmologists have proposed using voids as a specific tool for testing dark energy's behavior, the way a physicist might design an experiment in a vacuum chamber to remove unwanted interference. A region with almost nothing in it becomes strangely useful, precisely because there is so little else competing for attention. And yet, the honesty of the field requires saying plainly that no one has proven which explanation is correct. or whether both play some part. The growth of nothing may turn out to be a partnership between fading gravity and a pushing force we still cannot name. It may turn out that dark energy behaves in ways subtly different from region to region, something current theories do not yet predict. If you floated in that void a while longer, you would feel the universe's quiet answer settle around you. Unhurried, unfinished, patient enough to wait for better instruments and sharper eyes. The emptiness would hold its secret a little longer, and you would drift there with it, weightless, unbothered, waiting the way the void itself has waited for billions of years already. Picture yourself waking up each morning under a sky with almost nothing in it. No bright band of neighboring galaxies, no soft cluster of light, hinting at a busy corner of the universe. Just a few faint smudges, spread so far apart that entire lifetimes might pass before anyone thought to connect them into a pattern. This is what it might feel like to live on a planet deep inside one of the great cosmic voids. Your body would feel no different. Gravity would still hold your feet to the ground. But your night sky would tell a very different story than ours does. Astronomers have wondered about this kind of place for decades, because we are almost certainly not living in one. Our own Milky Way sits inside a supercluster, a crowded neighborhood by cosmic standards, threaded with other galaxies, close enough to see and study. If you traveled far enough in the right direction, though, you would eventually cross into open water, so to speak, a stretch of space where galaxies grow sparse, and then rare, and then nearly absent altogether. Some researchers have tried to imagine what science would even look like from inside a place like the Boötes Void. Without nearby galaxies to study, early astronomers on such a world might take much longer to understand that galaxies exist at all. The night sky would offer fewer clues, fewer bright anchors for measuring distance, fewer natural laboratories close enough to observe well. It raises a quiet question about our own progress. Did our crowded cosmic neighborhood help us learn what we know, simply by giving us so much nearby to look at? There is a deeper layer to this thought experiment, and it involves the expansion of the universe itself. Voids are not static rooms of empty air. The space inside them is stretching, and by most models, it stretches slightly faster than the average expansion rate of the universe as a whole. Matter, inside a void, feels a gentle outward pull toward the denser walls that surround it, like water being drawn away from an empty basin toward the edges of the room. Over billions of years, this slow drift could make voids even emptier than they already are, thinning out the few galaxies inside them even further. If this pattern is real and continues, it means the universe's structure is not fixed. It is aging into something more extreme, more divided between crowded filaments and increasingly hollow gaps. Some cosmologists see this as a natural outcome of gravity working alongside dark energy, the mysterious pressure that appears to be pushing the universe's expansion to accelerate. Others caution that our understanding of void growth still rests on simulations and models that carry real uncertainty. The exact numbers, how much faster, how much emptier, remain open questions still being tested against new surveys of galaxy positions. There is also the strange possibility that we ourselves live in a very mild, very shallow void, sometimes called a local void, a modest underdensity compared to giants like Boötes. If that idea holds, then our own vantage point may already be a little unusual, a little quieter than the universe's crowded average. It would mean the sky we grew up watching, full of galaxies bright enough to name, might actually be a gentler version of what most of the universe looks like from any random point within it. None of this changes what your body would feel standing on solid ground, wherever that ground happened to be. Gravity is gravity. Starlight still warms a face turned toward it, whether that light traveled past 100 galaxies or only a handful. But the story printed across the sky would shift enormously, and so would the pace at which any civilization living there might come to understand its place in the universe. A crowded sky invites cataloging, comparison, easy proof that other galaxies exist beyond your own. An empty sky invites patience, doubt, and perhaps a longer road toward the same conclusions. Whether the universe is slowly emptying more of itself out over time, or whether these voids will eventually stabilize into some quieter equilibrium, is still unresolved. The simulations lean toward continued growth. The observations are still catching up to confirm exactly how much and how fast. For now, it is enough to imagine standing under two very different skies, one dense with galactic light, one nearly silent, and to wonder which kind of sky is more common across the vast, still unmapped volume of everything that exists. If you lifted your eyes tonight and looked past the familiar stars of our own sky, you would be looking, without knowing it, toward the edge of something enormous. Astronomers call it the local void. It sits close to us, in cosmic terms, a vast stretch of space, with far fewer galaxies than the regions around it. Our own Milky Way sits near its border, close enough that its emptiness has likely shaped the motion of everything around us, including us. Light from that direction behaves differently than light from crowded parts of the sky. In a dense region, light gets passed from star to star, scattered by dust, bent gently by the gravity of countless bodies packed close together. In a void, light travels a longer, lonelier path. It leaves a distant galaxy and crosses millions of light years of near nothing before it reaches any eye, any lens, any telescope mirror waiting to catch it. If you stood at the heart of a void like this one, the sky around you would look thin. Fewer points of light, wider gaps of true black between them. That thinning is not just a visual softness, it shows up in the numbers too. Galaxy counts drop noticeably in the direction of the local void compared to the busier regions nearby. Some researchers estimate this underdensity has been strong enough to leave a mark on our galaxy's own motion through space, gently pushing the Milky Way, as if we are drifting from a place with less mass toward places with more. That drift adds to a puzzle astronomers have wrestled with for decades, figuring out exactly why our galaxy moves the way it does through the wider structure of the universe. Here is where the light itself becomes a kind of witness. As light crosses a void, it can lose a small amount of energy, climbing out of the gentle gravitational dips that still exist even in emptiness, and gain a little falling into denser regions beyond. This effect, tied to the changing shape of gravity across large regions, is one tool researchers use to test whether the universe's structure lines up with our best models. If the light does not behave quite the way those models predict, it hints that something about our understanding of these enormous empty regions may be incomplete. One idea proposes that our galaxy simply happens to sit in an ordinary spot, and voids like this one are common outcomes of how matter clumped and thinned across billions of years. Another view treats our position as something worth more suspicion. If we happen to live in a mild underdensity ourselves, some of what we measure about the universe's expansion, including the exact rate at which distant galaxies recede from us, could be subtly skewed by our own local surroundings. That possibility remains unresolved. It touches directly on long-standing disagreements over how fast the universe is truly expanding. Disagreements that different measurement methods have not yet fully reconciled. If you tried to travel toward the center of the local void, the change would come slowly, not suddenly. Galaxies would not vanish all at once. They would simply grow sparser with every million light years you crossed, like trees thinning at the edge of a forest, until only a few remained, scattered and distant, glowing faintly against a wider dark. Your instruments would need to work harder to catch their light. Your sense of scale would stretch, because the emptiness itself carries no landmarks, nothing nearby to judge distance against, only faint smudges of galaxies hanging far ahead. The colors would shift too, in subtle ways. Galaxies far across a void often appear slightly redder, their light stretched by the ordinary expansion of space during its long crossing. In denser regions, closer neighbors show less of that stretch, their light comparatively bluer, more immediate. Standing inside a void, you would be surrounded by red-shifted whispers of distant structure, with almost nothing nearby to break the pattern. What remains genuinely open is how typical our neighborhood is within this picture. Is the local void an ordinary feature of a universe full of such gaps, no different in kind from the countless other voids mapped across the sky? Or does our closeness to it mean our view of the universe carries a small, persistent bias, one that could shape everything from galaxy counts to expansion measurements? No survey so far has settled the question fully. For now, the honest answer is that we live near an edge we do not fully understand, watching light limp toward us across a gap whose true size, shape, and meaning remain part of an unfinished map. Close your eyes and picture a room full of quiet humming machines. That hum is the sound of a supercomputer working through the night, building a universe out of numbers. If you sat beside it, you would feel the low vibration in the floor, steady as breathing. This is how many scientists study the voids. They cannot travel to the Boötes Void or the local void in a spacecraft, so they build smaller versions of the cosmos inside a machine, and they listen for what those small universes tell them. These are called cosmological simulations. A simulation starts with a rule, almost like a musical score. It begins with the faint density ripples left over from the early universe, the same tiny unevenness that the cosmic microwave background shows us as soft patches of warm and cool. Then the simulation lets gravity play out across billions of simulated years, compressed into hours or days of computer time. Your own heartbeat would slow to match the patience this work requires, because the answers do not arrive quickly. What emerges again and again is something that looks remarkably like the sky we actually observe. Matter gathers into filaments and clusters. Wide, hollow regions open up between them. The simulated universe grows its own cosmic web, with knots of galaxies and long empty stretches, almost as if the numbers already know the shape of the real thing. This agreement is one of the strongest pieces of evidence that gravity, acting on those early ripples, can explain the pattern we see. But agreement is not the same as certainty, and the size of the largest simulated voids does not always match the largest voids astronomers find in surveys. Some simulations produce voids that grow to a certain scale and then stop, limited by how gravity behaves under standard assumptions. Real surveys, though, have found voids and superstructures that push past what many models predicted, structures so wide but light takes hundreds of millions of years to cross them. If you stood at the center of one of these simulated voids, the simulation would tell you how many galaxies should surround you, how bright the sky should look in every direction. Comparing that prediction to the real, quiet sky is one of the ways researchers test whether their rules are complete. One idea researchers explore is that dark energy, the mysterious pressure thought to be pushing the universe apart, might behave slightly differently inside a void than the simplest models assume. If that is true, simulations would need an adjustment, a new note added to the score, to match what telescopes actually record. Another idea holds steady with the standard picture, suggesting the discrepancies come from limits in how surveys measure very distant, very faint galaxies, not from any flaw in the underlying theory. Neither explanation has won out. The question remains open, sitting quietly between two competing songs. There is something almost musical in how these simulations are described by the people who built them. Some researchers speak of stretches of code as producing resonances, moments where certain patterns of matter repeat at particular scales, echoing like a low tone through the model. This is a way of speaking, a metaphor borrowed from sound, but it captures something true about the structure. The universe does not scatter matter randomly. It arranges itself in a rhythm, dense here, empty there, over and over, at scales so large that a single repetition can span more space than the human mind easily holds. Engineers, working with actual sound, have converted other cosmic signals, like the vibrations picked up from gravitational waves or the crackle of space plasma, into audible tones for public listening. Voids do not emit sound in that direct way, since sound needs matter to travel through, and voids are defined by having so little matter to carry it. But the comparison lingers because listening to a simulation run, watching its patterns evolve step by step, feels a little like listening for a signal buried in static. Researchers are trying to hear the shape of gravity's handwriting, the pattern beneath the numbers. If you leaned close to that humming machine tonight, you would feel its patient vibration and know that inside it, a small universe was quietly deciding where to place its galaxies and where to leave the space around them still. No one fully knows why the true universe chose the particular pattern it did, why the voids grew exactly as large as they are, or whether some subtle physics still waits to be found in the gaps between prediction and observation. The simulations get closer with every improvement, but the largest, emptiest silences in the sky still hold a little more mystery than the models can yet explain. If you sat quietly with a pencil and paper, you could write down the rule that built the cosmic web. It is not a long equation. Gravity pulls matter together, and denser places pull harder than empty ones. That is nearly all of it. And yet, from that one simple rule, the universe built galaxies, filaments, and voids the size of small superclusters. Cosmologists describe the early universe with a number called the density contrast. It measures how much a patch of space differs from the average. In the beginning, this number was tiny, often just 1 part in 100,000. Picture a smooth pond with only the faintest ripples on its surface. That faintness is almost impossible to picture, and yet it held the entire pattern of what was to come. A slightly denser patch has slightly more gravity pulls in slightly more matter. That matter makes the patch denser still, which pulls in even more. This is a feedback loop, and feedback loops in nature tend to grow, not stay still. Cosmologists call this gravitational instability, and it works like a small hill on a sand dune that slowly steepens with every gust of wind. Over billions of years, that slow steepening turned faint ripples into filaments thick with galaxies. But here is the quieter half of the same rule. If a patch starts out slightly less dense than average, it does not stay neutral, it empties further. Matter near it feels a weaker pull inward, and a stronger relative pull toward the denser regions nearby. Slowly, gently, that matter drains away, the way water drains from a shallow basin toward a deeper one. Some researchers describe this as running structure formation in reverse. Instead of gathering fuel, the region loses what little it had. This is one leading idea for how voids grew so large, so smoothly, and so consistently across the observable universe. If you tracked a single dim galaxy near the edge of a young void, you would watch it drift outward across billions of years, pulled by filaments it could not see, toward walls of matter far denser than its own quiet neighborhood. Its motion would look almost lazy, a few hundred kilometers each second, small compared to the scale of the space it crossed. And yet, that same slow drift, repeated by countless galaxies, hollowed out regions that would eventually stretch across hundreds of millions of light years. There is a ratio that shows up again and again in these calculations, something researchers call the void to filament density contrast. In many voids, matter density falls to perhaps 10 or 20% of the cosmic average. That is not nothing. It is a thin, quiet remainder, spread across a volume so vast that even a small amount of leftover matter can seem lost inside it. The mathematics allows for these numbers comfortably. What it does not fully explain is why some regions emptied so much further than others, or why certain voids grew wider than the models expect. This is where the simple rule runs into an open question. Small computer models, called simulations, take that early faint density map and run gravity forward across billions of simulated years. Many of them reproduce a web of filaments and voids that looks remarkably close to what surveyors observe in the real sky. That agreement is one of the most elegant results in modern cosmology, a confirmation that a rule this simple can build something this large. But the largest real voids, including regions like the Boötes Void, sometimes emerge a little emptier, a little wider than the average simulation predicts. Some researchers wonder whether dark energy, the mysterious pressure some believe stretches space itself, plays a stronger role in the later stages of void growth than current equations capture. Others wonder whether the simulations are simply missing detail at scales too small and too faint to model precisely. If you could freeze time and drift slowly through one of these expanding voids, your body would feel nothing unusual. No pull, no resistance, just the ordinary stillness of open space. But the numbers behind that stillness would be quietly at work, dividing space into rich neighborhoods and near empty rooms according to rules laid down almost 14 billion years ago. The equations are elegant, the outcomes they produce are strange, and the gap between the two, small as it looks on paper, is still large enough to hold an open question. For now, the mathematics offers a shape, a tendency, a direction, structure, formation seems to follow as it slows in emptier places. It does not yet offer a complete account of every void's exact size or edge. The rule is simple. What it built is not fully explained. And in that space between simplicity and mystery, the largest structures in the universe continue to sit, quiet, unresolved, and strangely beautiful. Picture yourself standing at the edge of a great empty field at night, unable to see where it ends. That is something like the position our galaxy may be in. Some researchers wonder whether the Milky Way sits near the edge of a very large, very faint underdensity, a stretch of space with fewer galaxies than the cosmic average. If you tried to feel the pull of that space around you, your body would sense nothing unusual. Gravity here still holds the floor beneath you and the moon in its slow orbit. But on a scale far larger than any of that, something quiet may be tilting the balance of everything nearby. This idea connects to what cosmologists call the local void, a vast low-density region that appears to sit close to our own galactic neighborhood. Its exact size and shape are still being mapped, and its influence on our motion through space is still debated. Some studies suggest this void may be pushing our galaxy along, adding a gentle nudge to the larger pull from denser regions elsewhere. Other researchers argue the evidence is not strong enough yet to say how much of our motion the void explains. The disagreement is not about whether we are moving. It is about how much of that motion belongs to a void's quiet shove and how much belongs to the pull of distant clusters. Think of the balance the way you might think of a marble resting near the rim of a very shallow bowl. A tiny push in one direction sends it rolling toward emptier ground. A tiny push in another direction sends it back toward the crowded slopes where galaxies gather. The early universe held fluctuations this small, differences in density so faint they would fit inside a whisper. Yet those small differences may have decided which regions became rich with galaxies and which regions became the hollow spaces we now map. If you had stood in that early universe, the unevenness would have been invisible to you, smaller than any shadow, smaller than any breath of wind. The fragile part of this story is how much rides on conditions that seem almost accidental. If the early fluctuations had been slightly stronger, the universe might have clumped into fewer, denser islands, leaving voids even larger and darker than the ones we observe now. If the fluctuations had been slightly weaker, matter might have spread more evenly, and the cosmic web we see today, with its threads and empty rooms, might barely exist at all. Some researchers see this as evidence that the universe's large-scale pattern depends on a narrow set of starting conditions, a balance easy to imagine tipping the other way. Others caution that we only have one universe to observe, so it is hard to know how sensitive that balance truly is. There is a personal version of this fragility as well. Earth sits at a very specific distance from the Sun, close enough for liquid water, far enough to avoid being scorched. Our atmosphere is a thin blue skin, only a few hundred kilometers thick, holding in warmth and holding out radiation. If you flew high enough, you would watch that atmosphere thin into nothing within minutes, the sky turning from blue to black as the air runs out. These small, precise conditions allow you to breathe, to feel gravity pull evenly on your limbs, to lie still and drift towards sleep. In much the same way, the density patterns of the early universe needed a kind of precision to produce galaxies at all, though cosmologists still debate how strict that precision needed to be. Some models suggest the universe could have supported galaxy formation across a fairly wide range of initial conditions. Other models suggest the range was narrower than it looks, with small changes leading to a universe with far less structure, or far too much, collapsing early into isolated clumps. Neither view has settled the question. The evidence remains incomplete, built from simulations that can only test so many possibilities at once. If you tried to sense this balance directly, you would feel nothing shift beneath you. The floor stays solid. Your breath stays steady. But somewhere far beyond the reach of any telescope's easy focus, a fragile arrangement of matter and emptiness continues to hold its shape, the way it has for billions of years. Whether that shape was inevitable, or whether it could easily have been otherwise, remains an open question tonight, resting quietly in the dark alongside you. Picture yourself floating at the center of a great void, 100 million light years from the nearest bright filament. Your instruments would say the space around you holds almost nothing, but almost is a word worth sitting with. Your body would drift in silence, and the darkness around you would raise a question that sounds simple, but is not. Is this place truly empty? Or have we simply not looked closely enough to see what fills it? Astronomers make a careful distinction between these two ideas, and the difference matters more than it might first seem. Empty means a region contains far less matter than average, measured by the light of galaxies we can detect. Unexplored means our tools may be missing something that is actually there. Void could be genuinely underdense, a true gap in the cosmic web, or it could be full of things too faint, too small, or too dark for our telescopes to catch. Both possibilities remain open, and both are being tested right now. Consider the galaxies we do find inside voids. They tend to be small, dim, and scattered thin across enormous distances. Some researchers wonder whether many more such galaxies exist, sitting just below the brightness our current instruments can register. If your eyes could somehow see every faint dwarf galaxy hiding in the dark, the void around you might look less empty and more like a sparse, quiet meadow instead of a bare, silent field. This idea is called the luminosity problem, and it has not been settled. Deeper surveys, using more sensitive instruments, keep pushing the faint end of the count a little further each decade, without ever declaring the search finished. Then there is the harder question of what we cannot see at all. Ordinary matter, the stuff of stars and planets and your own body, makes up only a small share of everything the universe seems to contain. The rest is dark matter, which does not shine, and dark energy, which does not clump. A void could hold dark matter in some diffuse, spread out form that leaves no visible trace. If that is true, calling the void empty would be a kind of illusion, built from the limits of light rather than the true state of space. If you could somehow weigh the void directly, using gravity instead of light, the number you got back might surprise you. Gravitational lensing offers one way to test this. When light from a distant galaxy passes near a void, its path bends slightly less than it would near a filament, because there is less mass to pull on it. Astronomers have measured this effect, and the results generally support the idea that voids really are less dense, not just less bright. But the measurements carry uncertainty, and the void's true mass, down to the last invisible gram, remains difficult to pin down. The evidence leans toward genuine emptiness, but it does not close the case completely. There is also the matter of scale. Some voids we have mapped might be even larger than we currently think, their outer edges blending into other underdense regions in ways our surveys have not fully traced. Cosmologists disagree about where one void ends and another begins, since the boundary is not a wall, but a gradual thinning of galaxies. Mapping that gradient precisely, across billions of light years, requires more data than we currently have collected. Future surveys, built to catch fainter and more distant galaxies, may redraw these boundaries entirely. None of this uncertainty is a failure. It is simply the shape of an active question, still being worked on by people who find it worth their careers. Every incomplete map is an invitation, not a dead end. The gap between what we have observed and what is truly there is exactly the space where new discoveries tend to appear. If you rested in that void tonight, you would be resting inside an open notebook, not a closed book. The pen is still moving. Some nights, the difference between empty and unexplored might collapse into the same thing once our instruments finally catch up. Other nights, it might reveal a universe stranger than the simple picture we hold now, filled with faint structures we have only begun to notice. Both outcomes are possible, and neither has been ruled out. For now, the void keeps its secret, patient and vast, while your body rests in the hush of not knowing yet. Picture yourself floating at the edge of a great void, watching the slow work of time move across it. Your body would feel no wind here, no pull of weather, only the faint tug of gravity from filaments so far away their light takes billions of years to arrive. If you could wait and watch, you would see the void doing something quiet but enormous. You would see it growing. This is one of the more settled predictions in an otherwise open question. Voids are expected to expand, not because something is pushing outward from within them, but because dark energy, the mysterious pressure that seems to stretch space itself, acts most strongly where matter is thin. Inside a void, there is little mass to resist that stretching. So the void grows, gently, over spans of time too long for any single mind to feel directly. Your body, if it lived 1 billion years, would feel the space around it thinning further, the distances between galaxies stretching wider than they are tonight. Meanwhile, the walls of the void, the filaments and clusters that border it, are expected to keep drawing matter inward. Gravity still wins there, pulling gas and galaxies together into denser knots. So the future of the cosmic web may be a sharpening of contrast. The full regions become fuller. The empty regions become emptier. Some cosmologists picture this as a slow separation, matter pooling into isolated islands, while the space between them turns into something close to true vacuum. Other researchers are more cautious, pointing out that our simulations only reach so far forward in time before the uncertainties in dark energy's behavior start to dominate the picture. We are extrapolating a trend, not reading a fixed outcome. This growth connects to something larger, the overall shape of the universe. Cosmologists have long asked whether the universe is flat, open, or curved back on itself, a question tied to how much matter and energy it holds. Voids offer one way to test this, because light bends slightly as it grazes the edge of a void or a supercluster. The pattern of that bending, called weak lensing, can reveal how mass is spread across cosmic distances. Some researchers use void shapes and sizes as a kind of ruler, checking whether the universe's geometry matches what our best models predict. So far, the picture holds together reasonably well, though small tensions remain between different methods of measurement, tensions that have not yet been resolved. There is a strange comfort in this. The void is not a wound in the universe. It is a working part of the whole structure, doing what physics expects it to do, even if we do not yet know every detail of how it began. If you could return to this same patch of space in 10 billion years, your body would drift through a region even quieter than it is now, starlight sparser, distances greater, the void having grown into something closer to true stillness. And yet, the story does not end in emptiness alone. New things are still forming even now, even here. Along the edges of voids, filaments continue to gather gas and dust into new generations of stars. Galaxies merge, slowly, over spans that dwarf any human lifetime. Somewhere in the crowded walls between one void and the next, a star is being born tonight. Its light not yet visible from Earth, its heat just beginning to press against the cold around it. The universe seems to hold both processes at once, hollowing out its emptiest places while still building brightness in its fuller ones. This dual motion, expansion in the voids and gathering at the walls, may be one of the clearest hints we have about the universe's long future. Some models suggest that as dark energy's influence grows stronger relative to gravity, structure formation will eventually slow everywhere, even in the filaments, and the whole cosmic web will begin to fade into a more even darkness. Other models suggest local pockets of density could resist this fate for a very long time. Islands of activity in an increasingly still sea. Which future is correct remains genuinely open. The data we have only covers a sliver of cosmic history, and the trends we see could shift as new surveys map fainter, farther galaxies. For now, the void keeps its slow pace, and we keep watching it from a great distance, trying to read its future from its present shape. If you rested here a while longer, your body would feel nothing change. No signal, no motion you could sense, but somewhere in that stillness, space itself would be quietly widening, carrying this question forward into a future none of us will see, though the universe, patient as ever, is already living inside it. If you lay very still and let your thoughts drift outward, past this room, past the sky, past the last galaxy your mind can picture, you would eventually reach a place where cosmologists themselves run out of certain answers. That is where we sit tonight, not in the void itself, but in the quiet room where scientists gather their data and admit, gently, that some questions remain open. One question they carry is about beginnings. The early universe was almost perfectly smooth, with only tiny differences in density from one place to another. Something in those small differences grew into the vast empty voids and crowded filaments we see today. The general story of gravity pulling matter into clumps is well supported, but the exact reason some regions became so empty and stayed empty across billions of years is still being worked out in detail. Your body, sitting here now, is made of atoms that trace back to that same smooth beginning. The calcium in your bones formed inside dying stars. The iron in your blood did too. You are old material, arranged for a short time into something that can wonder about its own origin. Another question is about scale. The Boötes Void and the other supervoids we have mapped are strange partly because of how large they are compared to what simple models predicted. Some researchers wonder if our understanding of gravity, tested so well nearby, might need small adjustments to fully explain structures this size. Other researchers think the standard picture works fine, and we simply need better maps and more patience. Both groups are still gathering evidence. If you traveled far enough into one of these voids, your body would drift for a long time before seeing anything at all, and the silence around you would carry no clear answer either way. A third open question concerns dark energy, the mysterious pressure that seems to be pushing space apart. It may be speeding up the growth of voids, stretching their empty interiors even as filaments cling to what mass they have. If that is true, future voids could grow larger than the ones we know now. But dark energy itself is not fully understood. It is a name for something we can measure the effects of, not something we can yet explain from first principles. That gap between measurement and explanation is one of the most honest gaps in modern cosmology. There is also the quieter question of where we sit in all this. Our own galaxy rests inside a relatively empty region called the local void, though it is far smaller and gentler than the great supervoids further out. Some scientists wonder whether living near an underdensity like this might subtly affect how we measure the universe's expansion. Others think our position is unremarkable, one ordinary neighborhood among countless others. If you could rise above the Milky Way and look outward, your eyes would find long empty stretches in some directions and dense walls of galaxies in others. Neither view would tell you, on its own, whether you are somewhere special or somewhere ordinary. What ties these questions together is not confusion, but humility. Cosmologists have built extraordinary tools. Redshift surveys map the positions of galaxies across billions of light years. Supercomputers simulate the universe from its earliest moments to its present shape, and still, when the maps are finished, there are gaps that resist easy explanation. That is not a failure of the science. It is simply where the edge of current knowledge sits. For now, lying here, your breath slows the same way it has for as long as humans have looked up and wondered about the dark spaces between the lights. The atoms in your body were forged in stars that lived and died long before the Earth existed. Those same physical laws shaped the vast voids sitting empty across the universe and shaped the crowded filaments beside them. You are part of that same unfolding process, small and warm and breathing, connected to events on a scale almost too large to hold in the mind. The open questions are not obstacles to comfort. They are companions for it. You do not need an answer tonight about why the voids grew so large, or whether dark energy will keep stretching them wider, or whether our own galaxy sits somewhere ordinary or strange. The universe has been patient for over 13 billion years. It can wait a little longer for us to understand it fully. For now, you can simply notice that you are here, made of old starlight, resting quietly inside a very large and very unfinished map. Your body is heavy now, resting in the dark, the way a galaxy rests inside its own quiet spin. We have spent hours walking through empty places bigger than anything we can truly picture, voids that stretch for hundreds of millions of light years, regions where galaxies grow rare, then rarer, then almost absent. We have asked why the universe grew this way, clumped here, hollow there, and we still do not have a full answer. That is all right. Some questions are meant to stay open a little longer. Think of the cosmic web one last time, gently, without effort. Threads of galaxies curving through the dark like frost on a cold window. Between those threads, the great soft hollows we call voids, quiet rooms in a house so large we have only mapped a few of its halls. You have floated through the Boötes Void in your mind tonight, felt the thinning of light around you, felt how small a single galaxy looks against that much emptiness. You have wondered whether those voids are truly empty, or whether they simply keep their contents hidden from easy view. Both ideas are still alive among the people who study the sky for a living. Picture a single blue planet now, turning slowly in that vast structure. Clouds drift over its oceans. Its coastlines glow faintly under a quarter moon. Someone is asleep on that planet right now, in a small room, under a blanket, breathing slowly. That someone is you. You live inside a modestly crowded pocket of the universe, a place cosmologists sometimes call the local void's quiet edge. Out, past our galactic neighbors, the density drops away, and the great hollow spaces begin. We do not know for certain if our little pocket is common or rare. It may be an ordinary corner. It may be something a little unusual. The universe has not told us yet, and perhaps it never will in any complete way. Let your shoulders soften into the mattress the way matter has settled, slowly over billions of years, into filaments and walls, and the dark spaces between them. No one rushed that process. Gravity pulled quietly, for a very long time, patient in a way nothing on a human scale can quite match. The tiny ripples from the early universe, impossibly small differences in density, grew into the grand pattern we now see stretched across the sky. Some scientists think dark energy pushed the voids to grow even faster, widening the gaps as the eons passed. Others think normal gravitational drift can explain enough of it on its own. The debate continues, calmly, the way a river continues to carve its path without any hurry at all. You do not have to solve any of this tonight. You do not have to hold the difference between empty and merely unexplored, or decide whether our sky is typical or strange. Let the picture rest in your mind instead, soft and unfinished, the way the universe itself remains unfinished. Somewhere out there, light is still crossing a void that has taken longer to cross than all of human history combined. It travels through darkness, past faint smudges of distant galaxies, and eventually, perhaps, it reaches a telescope and becomes a single point of data in someone's careful survey. That work continues night after night, adding a few more galaxies to the map, a few more voids to the list, filling in edges that were blank before. Somewhere else, a supervoid drifts along in majestic silence, containing perhaps a small handful of galaxies where a denser patch of space might hold thousands. If you floated at its center, your body would feel the same weightlessness you feel anywhere else in the dark. Nothing there would press against you or pull at you in any dramatic way. There would simply be quiet and distance, and the patient glow of a few galaxies scattered so far apart they barely seem to belong to the same structure at all. Let that image stay with you as you drift, a picture of vast, gentle spaces holding very little, connected by threads that hold almost everything we can see. The universe does not need you to understand it completely. It only asks you to notice it, once in a while, and then let your eyes close somewhere far past the edge of what any telescope has mapped. The dark continues, unbothered, patient, unfinished. You are held here, safe on your small spinning planet, inside a structure larger than imagination allows. That is enough for tonight. Rest now, and let the great quiet hold you the way it holds everything else. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.